All right, for graphical analysis of motion, which is what we are taking a look at, if we only look at the graphs, we can determine which way an object is moving and how fast, right? So what we took in notes was to recognize that if we have a distance versus time graph, and the graph is a horizontal line, we are at rest, right? We are in the same place as time goes on. If an object is going so fast, like the speed of light, right? And in the same time frame, we would almost say that it would be a vertical line, right? It would almost be instantaneous how quickly an object would travel. So this is the speed of light. So those are our two extremes of motion that we can have. At rest is the slowest, speed of light is the fastest that we know anything can be going, right? Anything in between is going to be a combination of those two. So if I were to walk forward at a rate of about 2 meters per second, my distance would be increasing over time. So let's say this would be 1 second, 2, 3, 4 seconds, and I'd walk a distance of maybe 5 meters. Oops, 2, 3, 4, 5. And every second I went 1 more meter, right? So in 2 seconds I was at 2 meters, 3 seconds, 3 meters, and so on. We'd get a nice diagonal line, right? But if I were to increase my speed, so this would tell me that I am moving away at a constant rate. If I apply the same scale, 1, 2, 3, 4, 1, 2, 3, 4, 5, and instead I travel at a higher rate, meaning every second I go every 2 meters, then 2 seconds I'd be at 4 meters, 3 seconds all the way at 6 meters. Notice that my line approaches more of this vertical. So along this line, I would say to compare these two, if I look from this one to this one, you would say my rate of change increased, or we would say our speed increased, right? In math, you might say our slope of the line increased. So by looking at these two graphs, what we are seeing is that the slope of a line implies speed, how fast something's going. If my distance is increasing over time, I'm moving away. So both of these, I am moving away from the reference frame as time goes on. But comparing this one to that one, I became closer to the vertical, which is the speed of light, so I must be getting faster as time goes on. If I instead decrease my distance over time, right, then let's say I started away from my reference point, and instead of starting at the reference point, I start my 5 meters, 4, away from the reference point. In that case, at time 0, maybe I was here, 1 second I was at 4, 2 seconds at 3, 3 seconds at 2, 4 seconds I was at 1, and 5 seconds I'm all right to the back. So I'd end up with this straight line in that direction. So what we clearly see as we go from this type of line to this, we get a negative slope, which implies that I'm walking towards my reference frame, right? So by changing the direction of my slope, I also change the direction of my motion. So again, the slope is determining speed and direction. If I were to go at a faster rate, again, that slope would increase, right? So even in the negative, the more I get to the vertical, the faster I am going, is what we're seeing in those 6 graphs that we were taking a look at. So this is the basis behind everything that we are doing. That's the slowest I can go if I have a horizontal line. The fastest is a vertical. Everything else is in between those two. If I have a negative slope, I'm moving towards my reference frame. Positive slope is away. Remember, the only way an object moves is if it changes its position with respect to the reference frame. So given this as our background information, we can now answer any questions regarding looking at a graph. We should be able to tell you which way an object is moving and how fast. So taking a look at this sheet, right? Let's blow this up a little bit, draw on that. So if we take a look at these, we can write our descriptions. So our description here would be the object is at rest, right? Because I'm at the same place as time goes on. In this one, our description would be I'm moving away from the reference frame with a constant velocity. So my speed is constant. So a lowercase v represents speed. Here, because I go in the negative, I am moving towards my reference frame, and my speed is still constant because the slope of my line is constant, right? So that's basically what we just repeated or saw on our notes. But as we look at these last three, they're a little bit different. So can we apply what we see in these first three to kind of describe these more complicated graphs? So clearly, this is still moving with an increasing distance as time goes on. So up to this point, I am moving away from the reference frame with a constant velocity, no different than I had up here. It's just shorter, right? However, when I switch here and I go like this, I'm still moving away. My distance is increasing, but with a lower slope. I'm approaching that horizontal line, so I'm getting slower. So I'm moving away, still with a constant velocity, but slower than the beginning. Right? Two ends in there. Now, when we take a look at curves, what I recommend when you do those is think of them as being made up of a bunch of little lines. And then you have to ask yourself, what's happening to the slope of those lines that make up the curve? So up here, my slope is horizontal. So all I can be doing is be at rest. So to go to something that has more slope, I am getting faster. But my slope is in this direction, so that implies a negative slope, which means I'm moving towards my reference frame. So in that case, I would say towards my reference frame with my velocity increasing, because if I was at 0 to begin with, I can only be getting faster. Then right in this segment right here, I go from more of a slope to less of a slope. Right? So in this segment up to this point, my distance is still decreasing. I'm still going in that direction. So I'm still going towards, but my velocity then decreases. I go from some velocity to the 0 velocity. I have no speed. Then I start heading in this direction, which means I'm going away from the reference frame. So this is me moving away, where my slope goes from nothing to something. So my velocity again must be increasing, and then it's going to decrease because I end up with that 0 slope. Excuse me. 0 slope, 0 velocity. All right, I'm going to pause, or you can pause the video and try this last one. Put in your little lines. So we're going from a horizontal to something, right? But I'm going in this direction, so I'm moving away, and my slope is increasing, right? So my speed is increasing, and then I continue to move away to the point where I stop. And then we'd say speed is decreasing, and then I stop. So in this one, I didn't necessarily say stop. You could You could say velocity is 0, but this one's clearly like in a very long horizontal line, right? So just as we take a look at the slope of a position curve is going to describe our velocity. So now we can actually go in and write, well, what's happening to our velocity here? So whatever I draw under my velocity graph would represent my slope of this. So however I describe what's happening is what I can be able to draw in my velocity graph. So what you're going to do in this second column is to draw your velocity graphs. So here I'm going to make a graph at each part because velocity can go from positive, 0, negative. So this is velocity versus time. So I'm going to put all those in there to get it all set up. Positive, 0, negative. All right, so I did that on all mine. So if you didn't do that, pause your video and go ahead and fill those in. And now we're going to say, okay, if I'm at rest, how much is my velocity? My velocity would be 0. So that whole time I have a 0 velocity. The slope of that represents your velocity. This has a 0 slope, so I have a 0 velocity. This has a constant positive slope, so that's how we would write this. Constant positive slope, right? So it's a constant velocity. Slope is a constant positive value. This one has a constant negative slope, so it's a constant negative velocity. So that's going to be down here. We don't know how much it is, but it's just a constant negative velocity. Here, I'm going away with a constant velocity again, right? So that's positive because I'm going away. And at that point where I drew that dotted line, I continue going away. So I stay in the positive, but a smaller value, right? So remember, I'm getting slower. That means I'm getting closer to the 0 value. This one's going to have multiple changes. In this direction, this is a negative part of the slope, and this is a positive. So at that point right here, I'm going to put a dotted line. That's when I switch from negative side to positive side. So I'm in here at the negative, and then I go to the positive. So what happened at first is I was in the negative with my velocity increasing. Increasing as I go more than 0, right? So 0 is the slowest velocity I have. So if I'm increasing, I'm going to go that way. Then I begin to decrease. So I must go back up to 0. So remember right here is our 0 velocity. Those 2 points match. And then I continue to move away, getting faster. And then I move away, getting slower, coming back to that 0 position right there. So the negative means I'm going towards, I was going towards, getting faster than slower, going away, getting faster than slower. Here, on my velocity graph, I'm moving away with an increasing velocity. So away is in the positive, so I'm increasing, then decreasing, and then I'm at rest. In the positive, because that represents away. So now, under graphical analysis, just like from here, slope is equal to speed, when I have a velocity graph, it is also true that on our velocity graph, if I have velocity versus time, we can have a line, and the slope of that line has meaning, and the slope of a velocity graph is equal to acceleration. Acceleration is the rate of change in your velocity, whereas speed, velocity, is the rate of change in your position. So this is graphing position, this is velocity. So as we take a look at this chart, right, and we want to do our acceleration, we want to think in terms of slope again. So now I'm going to go back and make my acceleration graphs, just like this. Acceleration can also be positive, 0, negative. So fill all of those in. Okay, so I filled in all my acceleration. So now what we are going to do is ask ourselves, what does the slope of this line give us? So this one has a slope that is 0, right? So that's going to have a 0 acceleration. This one also has a 0 slope, 0 acceleration. This one also has a 0 slope, which means 0 acceleration. All that 0 acceleration implies is that you have a constant velocity. It could be a 0 constant, it could have a value to it, it could be going in a different direction. All that it means is a constant velocity. It is not changing. On this one, we do have two different constant velocities, but they both have a 0 slope. What would be physically true is something has to happen here. There would have to be some kind of acceleration there, but we're going to recognize that as instantaneously happening. Here we have a negative slope, positive slope, and the same positive slope, and then negative slope. So this one's going to be a negative value, the same positive value for this extended time from here to here should be that positive constant slope, and then we jump back down to a negative slope. This one has a positive slope, constant, negative slope, and a 0 slope. So we'll have a positive slope, negative slope, and 0 slope for our acceleration graphs. All right, well, that completes the first page. Now, for your own practice, try each of these pages right here and see if you can look at these and work backwards. So the hint on these is, remember, a positive velocity. If it's positive, that means I'm moving away. If it's negative, then I'm moving towards. If it has a 0 value, I am at rest. So the easiest thing to do is think of the description first and then do the position graph. So this has a constant positive value. So I'm moving away with a constant velocity. So my description here should say away, constant velocity. So when I do my position graph, right, position versus time can only be positive. Away means I go from these 2 points, and that's what you want to do. And then say, okay, if I have to connect those 2 points, I must do it with a constant slope. So constant slope would be a straight line, right? And then this would have an acceleration graph that has no slope, right? So we'd have time, acceleration positive, 0, negative. That would have no slope. It's a straight horizontal line. So we're going to have a 0. All right, good luck. Think, think, think. Always refer back to what was discussed here as you're thinking, always thinking in terms of slope. Slope of the position graph gives you speed. Slope of a velocity graph gives you acceleration.